Hello everybody, welcome back to another Gorgeous Maths video. In this video, I'm just going to be going like a little 10-minute rant or something. I don't know how long it'll take me. On the thing I was talking about in test, and it's basically generalizing 21 dares. Now, I wasn't, okay, so I did generalize 21 dares for, you can add any number between 1 and n, and you have to get up to z. But I wasn't a Chad and managed to generalize it for any amount of players or for a general group. So, you know, I did do decently well, but I didn't manage to get it in its most general form, which would be in an abelian, in just a group G, with a general operation with an arbitrary amount of players. That would be the highest degree, but I did manage to do it in a specific ring known as the integers under addition, and yeah, this is what I'll be rambling on about for about 10 minutes. So let's see. So of course the premise of the game is, say for example 21 dares. Now basically that is, first say 20 wins. And you can add any integer, so n, between 1 and 3, such that n is an integer. So for example, the first guy says 1, the next guy can say 2, 3, or 4. And so on and so forth. So you alternate goes, player 1 says 1, player 2 says 4, for example. Player 1 says, say for example 5, and so on and so on, and the first person to say 20 wins. Now, I generalized this to a game in which I used the integers, but it should work for any real number, in which you can add any number n between 1 and x, such that n is an integer. In fact, we'll restrict ourselves to natural numbers. In fact, n and x are natural numbers. And the goal being to say z. Alright, so let's think about this. What does a player want? Well, what a player wants is for the player before him to say z minus x, because that way, in this way, he can just add x and say z. And similarly, he wants z minus x plus 1, x plus thingy, x plus y. And the only condition is that z minus x is less than or equal to this, and it's strictly less than z. So he wants the guy before him to say anything between z minus x and z. And the only way to force him to do this, alright, so think about it logically, we want him to have to say z minus x no matter what. And the only way to do this is by saying z minus x plus 1, right? Because then, the least he can do is add 1, in which case you get z minus x, and the most he can do is add x, in which case you get z minus 1, and anything in between you can get to z. So that's really good. So this is what you want. And now, we work backwards. If I say this, you're screwed, right? And so, if we similarly reasoning, if we subtract another x plus 1, then there's no way you're going to stop me from hitting this, and then there's no way you can stop me from hitting z, i.e. you're screwed. And so, if you just keep subtracting x plus 1, you should get to the first number you want to say. And then we found the algorithm for doing this. The algorithm is just keep subtracting x plus 1. So the really long way to do this is to keep subtracting. So say for example you're playing 69 first say 69 wins and you can add 5. Then one way you can do this is you can say 5 plus 1 is 6. Alright, so what's 69 minus 6? 63. And then minus 6 again is something. And so on up until you should get 3. You should get 3, I think. But actually, here's the key observation. You're actually just going through the congruence classes mod x plus 1. So for example, if we're using say the congruence class of z, in this case, we'll just define this to be the set of all x less than z, such that x is congruent to z. Sorry, I actually use a different number because this is confusing. N, such that n is congruent to z mod x plus 1. So this is all we're counting through. We're just counting through these congruence classes here, which I just defined like this. And so, the first number will be the infimum of this set. And so, what we want is to pick, so, the solution and actually I just came up with this notation. I'm quite proud of actually this notation. On the spot here is the first number to say is now the only time which player 2 wins is when the infimum of that set is 0. So again, so let's just say, so let's actually just put this on a side. Let's just remark. Set of all n, 0 is less than n is less than z. So n is bigger than 0 or equal to. Such that, actually if we set strict inequality here, then we have our solution actually. Because it's not allowed to say 0 first go, so that's good. So it's the set of all 0 less than n less than z, such that n is congruent to z mod x plus 1, where x plus 1, we'll just put that on the side here. And x is the number, actually we'll put x here. And x is the number which we can add, the maximum we can add. And so the first number to say is the infimum of z sub x, this set right here. And therefore, all you're doing is, say for example we use 69 as our example, you do 69 mod 6, and what's that congruent to? 3. And so there you go, that's the first number you say. So really that's all you're doing. So the only way in which the second player will win is when so if this is equal to, say, if this is equal to x plus 1, second player wins. If the infimum of this set is strictly less than x plus 1, x plus 1, the first player wins. And there we go. Less than, sorry, less. Alright, so let's take an example. Let's take an example. Alright. Example. So, yeah, let's just say z equals 69, x equals 5. Then, the first player wins. And, proof. The proof of this is, well, what's the infimum of 69 sub 5? Well, this is equal to 3. Since we just do 69 mod 5 plus 1, which is 69 mod 6, and what's that? The principal value, so to speak, is 3. And so that's the infimum of that set. And then, which is less than 5 plus 1. And so what you do is you go 6, and then the second number to say is, the second number, so the first number to say is this, and so actually overall, the nth number to say is, so having played n goes, yeah, having already played n goes, the next number to say is and so you do the infimum of this set plus n times x plus 1. Right? And why is this? Well, this is because, well, if you think about it, what you're going to do is infimum of z mod x plus x plus 1 is going to be your next move, plus x plus 1 is going to be your next move, and so on and so on and so on. And there's no way they can stop you from doing this, because if they only add 1, then you just add x. If they add x, you only add 1. And anything in between, you can still do it. And that's how you win. Alright, so, yeah, so to win, so you control your friends like this. So you can be like, if you're feeling mean, you can add a forfeit. And you can even, to prove it to them, you can get them to choose the number to add. And be like, okay, do you want to go first? And if they don't know this pattern, then as soon as you hit a number here, you don't let go. So, for example, let me come up with this number, 100. And you can add 10 each time. That seems quite fair. Alright, so what's the infimum of this set? Well, the infimum of 100 sub 10 is equal to, well, what is it equal to? What's 100 mod 11? That's really what this infimum is measuring. Well, that is going to give you 1. So this is the first play. Then, next one you're going to do 12. And so you're going to keep adding on until you get, and then you're gonna, okay, so the infimum, so you start off with 1, Then say, for example, your friend says, okay, that's cool, I'll go to 10. Then you say, okay, 12. Then you go to 23. Then you go, and you're adding it, and you're doing the plus 11 map every time until you get to 100. And there you go. That is how it's done. Now I've no idea how long that rant was. That was completely improvised. Because I figured it out, and then I tried to generalize it, and then when I failed my many attempts at generalizing it, then I decided I'd just ramble on about this, because I might as well make at least a video this weekend. So yeah, that's all for today, and yeah, you control your friends with this if it's just for light-hearted fun. You can just say, let's play a game, and then as long as they're willing to play, you crush them. You crush their souls. And if you're feeling a bit more mean, you can give them a forfeit. So like, I don't know. Do this XYZ if you lose, and then you let them pick the number so nothing sus is, so they think nothing sus is going on, and bam, you beat them every time. So yeah, it's a bit like 21 Dares in that sense. You can either, obey the original rules, in which whenever they say 21, you give them a dare, or it's just a fun game in which you crush their souls. Anyhow, that's all for today. Hope you like this. And by the way, all this notation is completely invented by me in the spur of the moment. I actually used a bit of a... when I first figured this out a couple of weeks ago, I used much sloppier notation with piecewise functions, and it only hit me while I was rambling on about this on camera. This is the notation to use, right? So yeah, actually, yeah. I guess I'll see you in the next video, in which I might be doing Love Math's request of cohomology operations. I'll do some stuff about. I might do some stuff about like stenoid algebras and stuff like that. Cohomology operations. Or I might continue the homotopical algebra series. Or I might start another series on commutative algebra or homological algebra. What I'm planning on doing is random videos like these every now and then, plus fans' requests, and 2 series at once. So I'm going to keep doing homotopical algebra videos. Eventually I'm going to go on to cool stuff like algebraic K-theory in that series. And I'm going to do some stuff about model categories later on. And I might do some stuff about commutative algebra, just because it's so useful to know commutative algebra. If you want to study like algebraic number theory, for example, or even algebraic geometry requires commutative algebra. So I thought it might be a helpful series just to add in the mix of my series. Or it could be, I might even continue topology. I really don't know, but I'm hoping to just pin it down to 2 series, and then continue going on with them for a while, and then while mixing in these random videos. Yeah, I guess I'll see you then. Goodbye.